Hello everyone. Today I'll be presenting a modified holistically nested edge detection approach to segmenting grain boundaries using synthetic images. In the material science research space, researchers are attempting to optimize the microstructure of materials by examining its microstructural evolution. The GIF on screen shows a microscopic example of a material sample undergoing deformation due to stress being applied to the sample. By identifying and characterizing the individual microstructures such as grains or cells, they can work to improve the mechanical properties of the material at large. However, this process can be very tedious and resource intensive. As such, it is extremely beneficial to automate these processes. As a starting point, I wish to identify unique grain structures of samples under a microscope. For this task, I've collected 6 sample images at 100 times magnification, as shown on screen. After reviewing past literature and the samples, I believe that identifying the grain boundaries would be a much easier task than identifying the actual grains themselves. And due to the contiguity of the grain samples as seen, we can then determine where the unique grains are. For the task of identifying the grain boundaries, I initially proposed a holistically nested edge detection approach based on a research paper of the same name. This approach works by adding side layers to the hidden layers in a deep learning model such as VGG16. This is followed by a fusion operation which essentially performs a weighted sum of each side layer output. These weights are also learned by the model. To facilitate training, I sliced each of the aforementioned samples into blocks of 100 by 100 pixels in size. I believe this would make it easier for the model to determine edge features as well as also artificially inflate the size of the dataset. This process created 540 block images, 81 of which were used solely for testing, and the remainder was divided into 70% training and 30% validation. I used a balanced cross-entropy cost function for training each of the side layer outputs. This was to account for the fact that edge pixels are grossly outnumbered by non-edge pixels in the data, and as such, there's a need to prevent the model from valuing higher false negatives over true positives. I then trained the data using the Adam optimizer. The sample was trained over 1,000 epochs at a learning rate of 0.001. For the edge probability map, I used an optimal data set scale with a threshold of 0.5. For the ODS, accuracy was determined by simply getting the pixel error rate. That is the number of incorrect pixels divided by the total number of pixels for the dataset. As shown on screen, the model received a score of 0.0068. As a reference, a score of 0.02 represents a score if all the pixels were marked as negative. As a qualitative example, I ran the model on one of my images with gray blocks highlighting data that was used in training and black blocks highlighting testing data. As you can see, the model performed relatively well on determining the edge pixels even in test cases. Nevertheless, the model shows quite a few false positives. I believe that the limited dataset contributes significantly to this. However, present constraints prevent the collection of more data, and even so, the data collection process, as mentioned before, is very tedious. As such, I again sought to artificially inflate the data. Whilst data augmentation techniques such as dropout, cropping, and geometric transformations are usually useful in this body of work, I found that these techniques do not account for the variations in grain samples and may distort the ground truths along with the images, as the techniques lack a meaningful understanding of what a grain looks like. As such, I propose the creation of synthetic data. As an example, I use Voronoi diagrams as a baseline to digitally draw new ground truths. From this, I use a series of techniques to fill the ground truths. For future work, I'll run models using a combination of both these real and synthetic samples. For future work, I'm also proposing a modified HAD approach, which includes a regression block to each side layer. The regression output will evaluate the sparseness of the ground truth. This may help in reducing the number of false positives. Based on simple testing already done on lower number of epochs, around 70 epochs, the model converges faster at the same number of epochs as we would have with the HED model. So this may prove to be very effective in the future. And this concludes my presentation. Thank you. Please be free to ask any questions if you have any.